Good afternoon. My name is Thorsten Kray, and I am the head of research and standardization with AeroCompact. It's a pleasure to be here, and I'll be talking today about state-of-the-art wind tunnel testing driving the design of PV racking systems. So, short information on my CV. I consider myself to be a very experienced wind engineer, having supervised several hundred boundary layer wind tunnel studies for roof and ground mounted PV racking systems. I did that with my former company, a renowned wind tunnel institute, where I have headed the department for testing of solar structures, other structures, and buildings in general. And with that, I think I'm sufficiently qualified to talk about wind loading on solar structures. Some brief information on AeroCompact. We are a supplier of racking for PV modules. Our headquarters is located in Austria, but we design our systems to the requirements of the global market. A brief outline of my talk. First of all, I will be digging into codes and standards with respect to wind loading on solar structures, focusing on rooftop PV. Then I'll be diving into wind tunnel studies for roof mount solar structures with regard to test methods, load sharing, analysis of wind tunnel, data and data reduction. Next up will be some comments on the structural design of PV racking systems. And then I'll be concluding and showing our involvement in code committees. Wind loading of buildings and structures is given in the wind loading part of the Eurocode, EN 1991-1-4, and in the corresponding national annexes. In each national annex, there's a section 1.5 defining the requirements for wind tunnel testing. A common misunderstanding is that only structures can be tested which are not subject of the standard, but that's not true. Basically, any kind of structure can be tested. Wind tunnel testing related to building structures needs to be conducted in boundary layer type wind tunnels, where the spatial temporal correlation of fluctuating pressures measured using high frequency sampling is covered. Moreover, the analysis of aerodynamic coefficients requires appropriate state-of-the-art methods. There are wind tunnel testing guidelines around in many European countries. In the Netherlands, we have the Kray 103 recommendation. In the German-speaking countries, there's a guideline by Windtechnologische Gesellschaft, which needs to be followed. But all guidelines have in common that they currently lack provisions for testing of solar structures. However, there has been a lot of research in the past 2 decades which has led to requirements which wind tunnel studies need to meet. These involve test methods, data analysis, data reduction, and also application of results. Moreover, there are modified analysis procedures which may be necessary if the model scale used in the testing does not match the scale of the flow simulation, and that is mostly the case. Further requirements involve zoning of wind loads of similar magnitude and pressure coefficients as a function of both tributary area or load sharing and building size. And with regard to the above, there are state-of-the-art standards, PV wind loading standards, which are the US building codes, AC 716/22, AC 49/21, and they all have in common that they are based on a guideline from California, the Structural Engineers Association of California Guideline PV2 2017. Here's the thing about the NEN 7250 and my main criticism, it was first issued in 2014, then reconfirmed like 2 years ago, but it is based on very limited wind tunnel test data by TNO, which dates back almost 2 decades. And there are a lot of issues. Roof zoning has been demonstrated not to be appropriate for roof-mounted structures. The building plan dimensions, roof height, width and length were insufficiently varied, and there was no study of array geometry. Usually when you see a wind tunnel test according to the NAN, the roof is filled with PV, not accounting for any stand-alone arrays somewhere else on the roof, such as in the deep roof interior. So not all of you may be familiar with wind tunnel testing. So here's a nice picture of a wind tunnel model. You can see one solar array, which is placed in one part of a large industrial building. The building itself is placed on a turntable, which can be rotated. And in that way, the wind flow can be simulated from any wind direction. So you have to imagine that the wind is coming from the background to the foreground. You can see there built-in obstructions, the so-called fetch in the boundary layer wind tunnel. This is how the flow characteristics look like that we use in our wind tunnel testing. On the top-hand left corner, there is the mean velocity profile matched by a power law. On the top-hand right corner, there's the streamwise turbulence intensity matched by a logarithmical fit. And on the bottom, one can see the spectral content of the flow, which is the spectral energy content of the streamwise velocity fluctuations. These diagrams are actually very important. The black lines show the measured data in the wind tunnel, and the colored ones are full-scale data by several researchers and adopted to different geometric scales. And one can see that on the right hand of the diagram, there's an overshoot of turbulent energy, which is safe at high frequencies. And in the low frequency range, there's an underprediction. And that needs to be taken into account in the analysis of pressure coefficients. And it's a common mistake that I've seen a lot in the real world, that this is not accounted for. The reason for that mismatch is actually that almost all wind tunnels around the world have been built for the study of conventional buildings at a scale of 1/200 to 1/400. And then just later they have been used for solar structures which are modeled at a larger scale, because the pressure equalization needs to be modeled because of pressure taps. So that is the reason. And yeah, this needs to be taken into account. It's very important. Based on wind tunnel tests, usually generic pressure coefficients are derived. There are also other formats of coefficients, but which have some disadvantages. And of course, the pressure coefficients need to be derived in a way that they can be applied to a range of buildings, not just for the building which was tested. When doing such generic testing, it is not required to mimic or to model specific nearby buildings, because that data is supposed to be used for multiple sites. There are, of course, exceptions. And there are further requirements. The models of solar panels need to be accurately scaled. Of course, the panel tilt angle, row-to-row spacing, aisles or gaps between rows need to be modeled. The height above the roof, the setback of the array from the roof edge, alignment of rows compared to the main axis of the building, deflector shapes, and where possible, the geometry of the panel support structure shall also be modeled. And of course, there needs to be a minimum number of panel rows which need to be modeled. So here's a close-up of a modeled array at a scale of 1/50. One can see some pressure taps on the top surface. There are also pressure tabs beneath on the underside, which cannot be seen. Here we have 9 rows, 5 are fitted with pressure tabs, and the others are dummies, and both portions of the array can be exchanged against one another in the testing. There is, of course, the pressure tubing underneath the wind tunnel test section. We don't have time, so I'm not going to dive into this deeper, but here we have a total of 250 pressure tubes. What is also important is to put the solar array in as many positions as possible on the roof to capture the different flow effects. The flow in the corner of the building is very different from the flow at the roof edges, and again different from the flow in the deep roof interior. So that's why we put the solar array in 7 to 9 positions in general on the roof. And it's also important to test for different building sizes. So usually we go for different building plan dimensions, varying the height. Parapets also have an effect on pressure coefficients. That's very important. Sometimes you can test for roof slope and sometimes even for open buildings, but in general enclosed buildings are tested because that is conservative. By enclosed I mean buildings with walls on all sides. Yeah, just briefly on the forces acting on solar panels and on deflectors, or in case of east-west acting on the east and west modules. The wind force is always perpendicular to the surface. There's usually an uplift on the PV panel, and on the deflector it can be a down force with a sliding load case, but it can also be an uplift force. So we usually have 2 components adding up in the horizontal direction, and the deflector compensates a little for the uplift force on the PV module. There are 2 load cases which govern the design and which must be analyzed. And these load cases are uplift and sliding. For the uplift load case, the maximum vertical force needs to be analyzed from the wind tunnel data. For the sliding load case, it's the vertical force plus a horizontal force divided by the static coefficient of friction. And as I've tried to explain, it is important to minimize the effects of different scales of the flow and of the model. Therefore, we use a method which has been adopted to this mismatch of scales. It's a modified Cook-Main method. There's also a publication on it. And the thing is that it refers the pressure coefficients to a 1-minute duration of velocity pressure, which is short enough to capture the portion of the spectral content of the flow at high frequencies where we have an overshoot of turbulent energy. And then these pressure coefficients are converted into the format which is used in the Eurocode. So all of this takes into account the mismatch of scales by analyzing the pressure coefficients in an appropriate way. Of course, load sharing is very important. Load sharing is defined as the system's ability to share loads acting on one solar panel with adjacent solar panels. It depends on the structural interconnection of modules, wire brackets, rails, and clamps. Load sharing can only be determined via testing. At AeroCompact, we follow a recently published guideline. It is called the Designer's Guide to Wind Tunnel Testing of Solar Racking Systems. I was also one main contributor to that standard. It has been published by Bundesverband Solarwirtschaft, the German Association of the Solar Industry. Yeah, and this is actually a very important diagram on the right-hand top corner. You can see on the vertical axis pressure coefficients, and they are plotted against a parameter called AN, the normalized tributary area. It is non-dimensional. And on the right-hand top side, you can see the equation. There is a term which is composed of the load sharing, circled in green, or the tributary area, and it is divided by another term which is representative of the building size. So that's why the normalized tributary area is non-dimensionless. And as you can see in that red term, the roof height is important, the width and the length of a building. There are some constants and some parameters determined from the testing. And this diagram, it means that the pressure coefficients, they scale with both, with load sharing and also with building size. And that is very important, and it's a common mistake that we find in the industry not to look at this. With regard to roof zoning, if we test for 9 different positions on the roof, we will come up with 9 different zones. But of course, we do that to capture all the relevant flow effects. The roof zone sizes must also scale with building size. They are not constant. And also within individual PV arrays on the right-hand side, it makes sense to distinguish between edge rows and inner rows and edge and interior modules in terms of pressure coefficients. Because the pressure coefficients, they vary a lot from zone to zone, but also within individual arrays. So now I would like to dig a little bit into the structural design of PV racking systems, but just a little bit because we have no time. For ballast design, the ultimate limit state concept of the Eurocode applies. And and it applies to the ballasting design for both uplift and sliding. And the abbreviation for that concept is EQU. The partial safety factor for wind loading is 1.5 according to the Eurocode. And that does not vary with different national annexes within the European Union. For dead load, there is usually a 0.9 safety factor. Sometimes it could be 1.0 in other countries, but in general it is 0.9. So all of these partial safety factors here are according to the Dutch standards. And we find it very important to indicate those partial safety factors in project reports because it will give a feeling of safety to the recipient of that report, to any third parties. I think that those safety factors should be made transparent. Now let's talk a little bit about the consequences class. The default value for the consequences class is CC2. In rare cases, you may have CC1 or CC3, but according to the Eurocode, it is CC2. And that consequences class is associated with a force importance factor, KFI, of 1.0. Now let's take a look at the wording that we find in the NEN. Actually, it is stated that solar structures can be attributed to CC1b. And that's simply not correct. If you take a look into the NEN 1990, it is stated that for Group A, to which the EQU, ultimate limit state concept, is assigned, you cannot use a KFI factor of 0.9, which you sometimes see in the industry. So I would like to briefly sum up and maybe jump directly to our commitment and code committees. I have been a main contributor to this guideline, the Designer's Guide to Wind Tunnel Testing of Solar Racking Systems. I have co-authored this CEOC PV2 standard, which forms the basis of the US building codes, which I'm very proud of. And I'm also the lead author of the update of the wind tunnel guideline of the German-speaking countries for buildings and structures. And for the first time, there's also going to be a section on wind tunnel testing for solar structures. And I hope that this code is going to be released this year. And with that, thank you.